Hi everyone. In this video, we're going to talk about the Kruskal-Wallis test that involves two or more independent samples. And so, as I said before, in the first video, the Kruskal-Wallis test is going to be the nonparametric equivalent of an ANOVA. So, when we want to compare more than two groups, so three or more groups, we use the ANOVA, which we learned in Chapter 14, or this Kruskal-Wallis test. Okay, and so the requirements for both of these are that we have independent samples of at least size 5, or at least for the Kruskal-Wallis test. Okay, the hypothesis for this test are that the distribution of the response variable is the same for all groups. The alternative is that some responses are systematically higher in some groups than in others. Again, this is really weird when you compare it to the ANOVA, because the ANOVA was that all of the group means are equal. But now we've got this weird wording, sort of, that the distribution of the response variable is the same for all groups, and then some of the responses are systematically higher than in others, which is essentially what we were saying in the ANOVA, but it's different because we're not involving parameters here. So I have an example here, and it's an example near and dear to my wife and I's heart, and it's tractor pulling. I don't know if you've ever seen this sport. It's crazy. You might think it's really dumb, and that's okay. But what happens is it's a competitive motorsport in which tractors drag a metal sled along a prescribed course. Okay? And people call this the world's heaviest motorsport. The tractors that drag the sled along are not tractors that you usually think of. Some of them have 4 or 5 motors on them at once that try to pull this tractor. So it's really quite interesting to at least look at the tractors. You might think it's sort of an interesting sport to have, but anyway, nonetheless, the sled contains a box filled with weights that's mechanically wrenched towards the tractor as the sled progresses along the course, making it harder for the tractor to keep pulling the sled. So this eventually causes the vehicle to lose momentum and stop. Okay, lose momentum and torque, and it's going to stop. They measure how you win in this sport is that the person who pulls the longest wins. Okay, so the distance from start to finish is measured in thousandths of an inch, so they have very precise measurements, and whoever pulls the farthest wins. Okay, and so there was a video here, but I won't show you this. Certainly, if you want to look up tractor pulling, YouTube or whatever video site that you use, and I'm sure you'll see some interesting examples. Okay, and so the question I want to ask is, does the length pulled differ for different brands of tractor? So there are a number of different brands that run in these competitions, and so it's ones that you'd kind of think of, John Deere, International Harvester, so on and so forth. And so they have big rivalries between them that the crowd really gets into for some odd reason. Okay, and so we have some data here. It's from the Great Lakes Farm Progress Pool in Boone, Iowa, from 2012. Okay, so the data is 18 lightweight superstock tractors. There are many different classes that these tractors can be in. Some of them, like for instance, the Shippensburg Fair, when the world opens back up, and you go, they bring old-time tractors, as you would say, the ones that you think of when you think of a like farm tractor, and they pull sleds as well. These are not like farm tractors. These are souped up, so to speak. And so there are multiple brands in the data. There's International Harvester, John Deere, and then what we're going to call other. There are many different ones. So there are some Fords, Case IH, this another one, New Holland, which is a Pennsylvania brand from New Holland, Pennsylvania. And then there's another one called Alice Chalmers. And so what we're going to do is look and try to see if there's a difference between the brands. And so we're going to go International Harvester, John Deere, and then other. Okay, because International Harvester and John Deere are the two sort of largest ones, and then the rest sort of fall behind. So we'll put them all into the other. And so here's the data of the 18 tractors that went. If you look at the names of the vehicles, they're always interesting. But you can see the vehicle name, the driver, where they're from, and the city state, the brand. IH is International Harvester, John Deere is JD, so on and so forth. Okay, and then the distance of how far they pulled. Okay, so I want to see if there's a difference in brand. So the first thing that we want to do is look at the data. And so since there are so few points, it's not really enough to make box plots to see whether they're different. So you might want to just plot the original data points. Excuse me. So we can look at the means for each group. International Harvester, John Deere, and then the other group, you see 342, 295, 258. And then you have, again, the sample standard deviations, 3, 52, and 94. Okay, so clearly, I think from what everyone can see from the graph, International Harvester seems to be doing the best, although overall, the winner of the competition looks like they are a John Deere, but the International Harvesters did well, and their average, their mean was much higher than the other two, and their standard deviation was much smaller than the other two. So let's try to perform a Kruskal-Wallis test. It's going to be very similar to the Wilcoxon signed rank that we saw before. We have n sub I, sample size of each group. N is the overall sample size of all the tractors together, or all the data points together, and then R sub I is the sum of the ranks for group I, just like it was before. And so the process for doing the Kruskal-Wallis test is nearly the same as the Wilcoxon signed rank. You pull all the samples into one, keeping track of where they were from, which sample they were from, assign the ranks, and then calculate a test statistic based on the ranks. The only difference from the previous video to this one is the test statistic, how we make it. So for here we had 5 International Harvesters, 5 John Deeres, and then 8 others. So big N, or capital N, is 18. And so we need to rank them. And so I've done the ranking over on the right in pink. And then we need to calculate R for each group. So International Harvester, 73. John Deere, 42. Others, 56. Okay. Clearly, the high and low rankings are not equally distributed among the 3 groups. Okay. Clearly, International Harvester has higher rankings than the others. Now, we have everything we need to calculate our test statistic. So the test statistic for the Kruskal-Wallis test is that. Okay, 12 over n times n plus 1 times the sum of r1 squared over n1 minus 3 times cap n plus 1. Okay, we don't need to worry about where the heck that test statistic came from, only that we need to use it. Okay, and so we calculate that test statistic. It's 6.529, and then the question becomes, what the heck do we do with the test statistic? Well, like any other test that we've done so far, we need to calculate a p-value. And to calculate a p-value, we need some distribution. And I sort of glanced over or washed over the distribution type thing for the Wilcoxon signed rank test, but we'll go into a little bit more depth here. The exact distribution of H under the null hypothesis is actually quite complicated. And so it's way over the level of this course. But what is a useful approximation is the chi-squared distribution. Okay, and so that's what most people use. So it's common to use the chi-square approximation, with the degrees of freedom being the number of groups that we have minus 1. So remember, for the chi-square distribution, it's defined by its degrees of freedom, okay, or it's parameterized by its degrees of freedom, which is the number of groups minus 1 in this situation. And so, again, we're going to use R to do the calculations and find the p-value and such, but Minitab can do this as well. So here it is in R. As usual, things are going to be very simple in R. Kruskal.test is going to do the Kruskal-Wallis test. Okay, we give it something interesting that's sort of unique to the R language. It's telling it what the relationship is that it wants to test, Brandis tractors. And so if you go down here, we'll see that we have that chi-squared value, the test statistic that we found, 6.5298, with 2 degrees of freedom because it's the number of groups minus 1, and it turns out that the p-value is 0.0382. So if we were testing at a 5% level of significance, we would say, yes, there is a difference. Or rather, what we should say is that, yes, the p-value is less than alpha, so we reject the null hypothesis. So formally, we'd say at the 5% level of significance, we reject the null hypothesis. There is evidence that the distribution of length pooled is not equal for all brands of tractors. And if you remember back to the ANOVA, that's all we could say. I often referred to the ANOVA as an overall test of significance, whether there was a difference or wasn't. That's the same thing here. We don't know which ones are different, but we may want to know that, but the Kruskal-Wallis or ANOVA aren't telling us that. Okay, so in fact, that's all we can say. Certainly to our eyes, it looks like the International Harvester brand was best, but we didn't test for that. And so we'd have to do some type of multiple comparisons procedure, which we talked about at the end of chapter 14, if we wanted to see what was specifically different. Okay, and so that's the end of what I want to do for chapter 15, and it's the end of new material in the course. So congratulations, you've made it.